Work is done on an object when a force causes the displacement of the object. Imagine that your car has run out of gas and you have to push it down the road to the gas station. If you push the car with a constant horizontal force, the work you do on the car is equal to the magnitude of the force F times the magnitude of the displacement of the car. Using the symbol D instead of delta x for displacement, we define work for a constant force as work equals force times distance.
Work is not done on an object unless the object is moved with the action of a force. The application of a force alone does not constitute work. Work is done only when components of a force are parallel to a displacement. When the force on an object and the object's displacement are in different directions, only the component of the force that is parallel to the object's displacement does work. If your force is at an angle, only the horizontal component of your applied force causes a displacement and contributes to the work. If the angle between the force and the direction of the displacement is theta, work can be expressed as follows: W equals Fd cosine theta.
Kinetic energy is energy associated with an object in motion. The kinetic energy of an object with mass m and speed v when treated as a particle is given by the following expression. Kinetic energy equals 1/2 mv squared. Kinetic energy is a scalar quantity, and the SI unit for kinetic energy is joule. Kinetic energy depends on both an object's speed and its mass. The net work done on a body equals its change in kinetic energy. The net work done by a net force acting on an object is equal to the change in kinetic energy of the object. This important relationship, known as the kinetic energy theorem, is often written as follows: net work equals the change in kinetic energy.
Potential energy is associated with an object that has the potential to move because its position relative to some other location. Unlike kinetic energy, potential energy depends not only on the properties of an object, but also on the object's interaction with its environment. Gravitational potential energy depends on height from a zero level. Gravitational potential energy can be determined using the following equation. Gravitational potential energy equals mass times free fall acceleration times height. The SI unit for gravitational potential energy, like for kinetic energy, is the joule. Furthermore, gravitational potential energy depends on both the height and the free fall acceleration, neither of which is a property of an object. Elastic potential energy depends on distance compressed or stretched.
The rate at which work is done is called power. More generally, power is the rate of energy transferred by any method. Like the concepts of energy and work, power has a specific meaning in science that differs from its everyday meaning. If the work done on an object is W in a time interval delta t, then the average power delivered to the object over this time interval is written as follows: power equals work divided by time interval. The SI unit of power is the watt, W, which is defined to be 1 joule per second. The horsepower, HP, is another unit of power that is sometimes used. 1 horsepower equals 746 watts.